Welcome back. Before we actually derive the equation for a tangent plane to a surface, we need to develop some tools to understand what derivatives of vector-valued functions look like. So in particular, if I have a vector-valued function r of t, and I want to take the derivative of the thing, how do I do it? So remember that a vector-valued function r that goes from some subset of r, so a single variable input, into, in this case, r3, so 3 components of the output, could be written parametrically as x of t, y of t, z of t, aka a single variable input, 3 outputs, where each of the components is given as a single variable function, which is really exciting. If we say that each of these components is differentiable, then looking at the individual derivatives is a Math 1A problem, and the question is, how do you map this back if you collect them in vectors? So how would you get the slope of a tangent line in R3? The first hint is to remember there's no such thing as a slope of a line in R3. Slopes correlate to directions. Dun dun dun. We'll see what we talk about in a second. In order to construct a tangent line to the curve r of t, what we really want to do is figure out a way to define a derivative of this vector valued function. As always, to define derivatives, we focus on a 5-step program to salvation. In this case, we're going to graph the curve. That curve is defined by r of t. We're going to find 2 points on the curve and draw a secant line through those points, which in this case, we're going to call a secant vector through that vector valued equation. So a secant vector value equation for a line through those points. And then we're going to measure the slope, but remember, slope corresponds with direction of that secant line. And then we're going to transform the secant line into a tangent line using the appropriate limit. And of course, we'll construct the derivative as the slope, or in other words, the direction of the tangent line. And what I mean by this is, if you think about the secant line is going to be given by some point plus a scalar multiple times a direction. And this is the direction that we're going to produce. The direction of the secant line in the limit will be the direction of the tangent line, and we will call that direction the derivative of the vector valued function. Pretty cool, right? All right. Let's start with part 1, step 1 of this 5-step process to salvation, which is to graph the function output for the curve. Remember that the graph of r of t will be a curve by definition, so just by parametric plotting this sucker, we're done with that one. Yay! There was much rejoicing. Yay! Step 2 was to, okay, so here's the curve. There it is. Boom, 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 boom. All right, that's the graph of the curve. And then step 2 was to pick 2 points. Perhaps we should actually I've used some kind of funny notation. Maybe we should adopt the notation we used previously. We'll call that first point P0, and we'll call the second point P. And these literally come from choosing 2 different values of the input. One of them we'll call t, and the other one we'll call tau. So here I have a curve in R3. I pick 2 values along that curve, and then I create a secant line through those 2 values. And remember, the secant line is going to be given by, I don't know what you want to call this thing. Maybe we call it like S. And then we're going to need some, here this t is a specific variable value for the exact point P naught. and then this tau is a specific variable value for the exact point P. So if I was going to do S, I need some dummy variable, and maybe we call that dummy variable, I don't know, alpha. So that's just some scalar, and this alpha is going to be a point, excuse me, this secant line is going to be through a point, and of course the variable or the parameter of this thing would be like alpha times some vector v, which is the direction vector, and then we'll say that the direction vector is the vector that connects P naught to P. Do you see it? So if I were to take the entire secant line, I'm actually taking the line that connects these 2 points, this direction through this point, where alpha is just a set of all scalars there, right? So that gives me parts 1 and 2. To measure the slope, I've actually given you a major hint. So step 3 was to measure the slope. Well, we just said that the slope of this thing is going to be the direction. Right? This is the major difference between lines in R2 and lines in Rn. In R2, we say that lines have slope. In Rn, we say they have direction. But they're the same concept, right? So here, when we say measure the slope, perhaps you want to call this vector v, the vector that goes from P naught to P. Well, that will be the slope of this thing. Right? That's going to be the direction that we're looking at. And that's the exact direction of the secant line. When we one of the really interesting things about this is when we write v, so here v would be given by the difference between x of tau, y of tau, z of tau, minus perhaps what you want to call this is x of t, y of t, z of t, because again, these are the individual coordinates of this one. This was when the value was t, and this was when the value was tau, which means that we could actually write individual components as x of tau minus x of t, y of tau minus y of t, and of course we'll call this thing z of tau minus z of t. And what's really cool about this is that because direction is defined to be any scalar multiple, we could also define a vector, I don't know, perhaps we call it u, which is 1 over t times the vector v. And of course, we're going to assume that t is non-zero. In fact, why don't we do this? Why don't we let the scalar that we're going to multiply, we'll let that scalar be tau. So whatever this value is, assuming that it's non-zero. So here, this is the t, this is the tau. Let's multiply this. Notice this would be in the same direction. This is the same direction as the vector v, because it's just a scalar multiple times v, and the one assumption that we've made is that tau is not equal to 0. Which is kind of what we can control, because this was the point at which we were going to take the derivative. This is just some other point. So if this point happens by setting t equals 0, then just force tau to be non-zero. And what happens here when we actually do this calculation out, we're going to have x of tau minus x of t divided by tau. Do you see a derivative there? Isn't this freaking amazing? This is just so awesome. Okay, then we got y of tau minus y of t divided by tau. And then finally, we've got z of tau minus z of t. Rookie Anderson. Look at this. I didn't give myself room here. Sorry about that. Okay, so now this thing would also be the direction of the secant line, but it's scaled by the appropriate scalar. And the reason is these should remind you similar to secant line slope for x, a single variable function, right? I take the difference in slopes of two things and then I divide it by the length along that direction. All right. So that's now the slope of my secant line. And in order to get the slope or the direction of my tangent line, what I'm going to do is to force the point P towards the point Q. So here, this was the direction of my secant line. And why don't we just say scaling it by U? So scaling it by 1 over tau. So what I'm going to do is I'm going to force this point this way. So what's going to happen when I do that is I'm going to get a direction that is closer and closer and closer to the direction of the tangent line. And we will say that the tangent line direction is given by taking the limit as tau approaches t of the vector u, which of course we just said this is going to be the limit as tau approaches t of, and this is where I have to be careful, x of tau minus x of t divided by tau, y of tau minus y of t divided by tau, and then this of course would be z of tau minus z of t divided by tau. I don't know if you see this, but I could have written this as tau approach t of r of tau minus r of t all divided by tau. Do you see that? That I can factor these out and I can look at this as a scalar value. I would encourage you, if this isn't clear, write about 3 or 4 sub-steps to make it super clear for yourself. Well, it just so happens that this is actually the derivative of r at t. That's the direction of the derivative. And of course, you could say let h be equal to the difference between tau and t. And if you do this, you could rewrite the derivative or the direction of that vector as the limit as h goes to 0 of r of t plus h minus r of t all divided by h. And I'll give you a major hint on how to work this out. Above, I told you that you should really try to make sure you understand that step. And here's the hint that I'll give you. This is going to be x of t plus h, y of t plus h, z of t plus h. And then this would be x of t. Oh my God, I'm such a rookie. Y of t. I'm so sorry. Z of t. So at home, you should pick up a rotten tomato and throw it at your screen for the fact that I am not doing this very beautifully. So I'm going to go ahead and pull this. I'm going to break my cardinal rule and not line up my equal signs. Okay, so this would now be the limit as h goes to 0 of x of t plus h minus x of t divided by h. And then this is now y of t plus h minus y of t divided by h. And then finally, I've got z of t plus h minus z of t over h. And then this is where I hope that you just are flabbergasted, and that's a really funny word. Check this out. If I bring the limit in, do you see that this is the limit of this thing, the limit of this thing, and the limit of this thing? And do you see that indeed that is going to be x prime of t, y prime of t, z prime of t? Which means when you take the derivative of a vector valued function, so this is the derivative of r of t, which we called r prime of t, which we said was the derivative of these 3 scalar valued functions. So you call this thing x of t, y of t, z of t, that derivative comes into the individual components. Can you believe this? So here we've got d dt of x of t. Here we've got d dt of y of t. And then here we've got d dt of z of t, right? Which we just said was x prime of t, y prime of t, z prime of t. And let me just interpret this for a minute. what this means is if you have some curve, so this is the graphical representation of this mathematical analysis, which you all are super sophisticated, right? The fact that you're even watching this video means that you probably are starting to sacrifice other parts of your life to think about math, which is really exciting. The power is yours. So the whole idea here was that we had some point P naught, we had some other point P. We looked at the direction of a secant line, which we defined to be the direction of the vector that connected those two. And then we took a limiting process and we constructed, so if this is the graph of R of t, we could look at this vector valued equation for the tangent line to this graph. And the direction of this thing would be R prime of t, which literally just came from taking the derivative of each scalar valued function of these components. So this right here, the direction, this vector that starts at P naught and goes off in this direction, we called that thing the derivative of the curve. Notice the last thing I'm going to say, I'm going to repeat it one more time. Direction in R3 is equivalent to slope. So when you take the derivative of a vector valued function, you're looking for the slope of the tangent line, which is the direction of the tangent line, which is encoded by this vector. This sets us up for a beautiful description of how to create tangent planes to curves. That's exactly what we'll do in the next video. See you there.